No, the channel on YouTube where I teach. Is there someone who have ever seen my YouTube channel? You've never seen? Yes. Means you have been left behind. Because everything, all the topics that are posted on YouTube, you can watch me while I'm teaching in my school. I'm a teacher. I teach. So we're going to talk about rates of reaction. Rates of reaction. I'll try a long time without getting a job. Okay, we're going to talk about rates of reaction, right? This topic, sometimes it confuses people because the name of the topic, it is called rate of reaction, right? Yes. But within that topic, rate of reaction, there is a section that is called rate of reaction. Then there's another section which is called chemical equilibrium. You understand? So it is called rate of reaction, everything, the whole thing. But within the whole thing, there is a small section on itself which is called the rates of reaction. You understand? So we're going to start from the rate of reaction. Just for example, as I told you, I'm not teaching, we're just going through and we explain some few things, right? Let me see if you do have the confusion. You see, this is maybe it's the formation of the product. Can you see the formation of the product? You see the line becomes straight here. Can you see? Yes. Is there someone who can tell me why is it straight? Then what's happening? Why do we have a straight line here? Like there's a slope, but we end up forming a straight line. Who can tell me what is happening here? Maybe from A to B. What is happening from A to B? Guys, because you are too quiet. So let's continue. I'm saying that you can see that there is a straight line. Who can tell me what is happening on the straight line? This is from A to B. What is happening? Is there someone want to tell me? Okay, tell me. Where there's a straight line, what does it mean? It has reached equilibrium. Do you agree?
Yes.
Do you agree?
Yes.
Incorrect. It is not correct, right? It is not correct. Then we're going to capitalize on that, right? Correct. That is correct. Okay. So, as I'm telling you that this topic is divided into two, right? There is a section that is called the chemical equilibrium. In chemical equilibrium, the straight line, it means it has reached equilibrium. But with the rate of reaction, the first part which is called the rate of reaction, there is no such thing of equilibrium, right? Yes. Okay, we are fine. Then let me teach you what is happening. The rates of reaction. When we talk about the rates of reaction, we're talking about how fast or how slow a reaction is occurring. We're concerned about that. When we say rate, we're talking about, is this reaction occurring fast? Is it occurring slow? The word rates of reaction talks about the speed at which the reaction is occurring. It's either the reaction is very fast or the reaction is slow. You understand? Yes. Let me give you an example. You know, inside of our stomach, there's a reaction that is occurring, right? That's why at the end of the day, we get a product and we go to the toilet. It's because it's a reaction. We go to the toilet and we poop there, right? Because there is a what? It's a reaction, right? Yeah. Do you know that reaction, I can make it fast? You know what I can do? I put soda in your food. The cooking soda. You know it? What will happen? You'll have a running stomach, right? Yes. The rate of reaction will be faster. The rate of reaction will be faster, the rate of reaction, because I've put cooking soda, right? Yes. So when we talk about the rates of reaction, we're talking about is either the reaction becoming faster or slow. So this topic of rates of reaction is concerned about a reaction occurring faster or slow. It means there are things that you can do to make the reaction to be faster. There are things that you can do to make the reaction to be faster or slow, right? Yes. As I've told you that, I've put soda. When I put soda, the reaction in your stomach will be faster. Did you see? Yes. Okay, it's fine. So now, Now, we know the definition of rates of reaction. It says that is the change in concentration of product or reactants, right?
Yes.
Reactants per unit time. Per unit time. Whereby mathematically we can write it, rate of reaction is equal to change in the concentration of product, alright, P over change in time. Or rate of reaction is equal to change in the concentration of reactants per unit time. This P stands for, you know that the corner, the bracket, they represent concentration, right?
Yes.
If I don't want to write concentration in words, many words, I'll write corner brackets. The corner bracket, they mean concentration. So this formula and these words is the same thing. It's the change in the concentration of product per unit time. Okay, well, good. We won't stick to the definition. So what will happen? It means during a reaction, the concentration of reactants is going to change, right? Even the concentration of product is going to change. Do you agree?
Yes.
Okay, fine. Then what is the reactants? The reactants, these are the things that we start with, right? Let's say we add A and B, right? And we form what? We form C and D. I'm giving you an example. Reactants, these are things that we mix. When we mix those things, we're going to form a what? A product. Like let's say we have juice. We have juice, right? We add it with water, right? We're going to form what? That nice juicy taste, right? Let us call it juice again. You know it, right?
Yes.
So we start with two things. The all things that we start with, we call them reactants, you know, right? Then we form the product. So let me just draw a graph that represents that. Let me just draw a graph that represents that. What will be happening to the reactants? What will be happening to the reactants? The reactants, these are the things that we start with, right? The things which we're going to add together. What will happen? It means during that process, they will be getting used up. To be used up, it means they will get finished. They will get finished. As they get finished, what will be happening to the product? They will be formed, right? Yes. Guys, I prefer people to see these things in their mind and to talk. Don't keep quiet. Guys, isn't it? The reactants, these are the things that we start with. You saw that? The product are the things that will come out. You saw that? So what is happening to the reactants? As I mix the reactants will be finished and we will no longer have the reactants. We'll have the product. You understand?
Yes.
You understand, right?
Yes.
So here is a graph. It means the product, as look at the reactants. The reactants are doing what? Are decreasing. Let's say this is changing time. This is molecules. Moles. Moles is molecules, right? These are molecules, right? What is happening to the molecules of the reactants? They're decreasing, right?
Yes.
Because when we take two things and we mix them, those things, they will get finished. Why are they finished? Because they formed a new thing. You understand?
Yes.
Then what is happening to the... So it means these are reactants. These are what? Reactants. Why is the graph going down? It's because they're getting finished. And as they get finished, what is happening to the product? They're getting formed. You understand?
Yes.
So it means the product will do what? Will increase. Will increase. So it means this is a product. And it is true, right?
Yes.
When we have two things, we start with two things, right? Let me give you an example. You know flour. Flour, the one we bake, not bloom. Flour, you know it, right? Let's say I take flour, right? I put sugar, milky, all the things which we use. We want to make the scones, right? Our reactants is what? What we'll start with, the flour, the milky, the water, all those things are called reactants. We mix them, right? We put it in the oven, right? Tell me, will we have flour at the end?
No.
It means what happened to flour? It get used up. To be used up is to get finished. It got finished, but to show that we're scientists, we don't say got finished. although it's correct, we say it got used up. So to get used up, it means it got finished. As it gets finished, we will no longer have flour. You can't take a scones and you say this is a flour. You can't see it, right?
Yes.
What do you have? The scones. It means the scones is a what? It's a product. The flour is the what? The reactant. So what is happening to the flour? Flour was decreasing because we were baking the scones, right? What about the scones? They were increasing because they are the product. Can you see?
Yes.
So this is the graph that represents the rates of reaction. Remember I said the rates of reaction were concerned with the what? The speed, right?
Yes.
Is this reaction occurring faster? Is this reaction occurring slow, right?
Yes.
You know the reaction in our stomach is a bit slow, right? If I can make it faster, just put cooking soda or Brooklands or castor oil, then the reaction will be faster. You see someone going to the toilet a lot more, right? So when you see someone going to the toilet a lot more, just know that the rate of reaction has increased. The rate of reaction has increased. One good, right?
Yes.
Listen, let me call you my babies. That's how I call people. There's a difference between the rate of reaction and chemical. Don't mix. Even in the question paper, the first question that will come, rates of reaction after chemical equilibrium. So don't confuse them. So look, you see there's a straight line here. Do you see? Let me explain what it means. It means we started with what? We started with reactants, right? Oh, let's say we want to make bricks. You know bricks? We're going to have cement, right? We add it with sand, right? And it produces bricks. As the bricks are produced, don't copy these things of cement. I'm making you to understand. It means when you want to give the answer, right? The picture that must come in your mind is cement and the brick. You'll get the correct answer. You understand? Eh? I'm talking about these things of cement and brick so that you can understand. I'm bringing it home. Are we good?
Yes.
Okay. Sand plus cement give us bricks. So as we are making the bricks, what will happen to cement and sand? It don't get finished. Am I wrong?
Yes.
That's why cement and sand they are getting finished. That's why they're getting used up. They're decreasing, right?
Yes.
They decrease until they reach a point where they remain the same. You understand?
Yes.
Look at here. What is happening to bricks? As we finish the sand, the bricks are increasing, right?
Yes.
They're increasing until they get to a point where they form a straight line, right?
Yes.
You know what is happening where there is a straight line? You know, if isn't it the numbers here, right?
Yes.
The numbers 0, 1, 2, 3, 4, 5, right? You see here, at 5 they are stopping. Can you see?
Yes.
You know what it means? It means, look, the bricks, they are at 1, right? They increase. They get to 2, right? They get to 4, right? But when they get to 5, you know what will happen? They become 5. Time is moving forward, right? But the number of bricks that we have, they are what? 5. They are no longer increasing. You know why? It's because we are no longer forming bricks. That's why bricks are remaining in the same place. We are no longer forming what? Bricks. So you know this line, you know what it represents? It says that reactants are used up. You can write this. Reactants are used up. Remember, what formed the product? What is it that we use to form the product? So it means when the reactants are finished, will we have more product?
No.
When the reactants are finished, we're no longer forming what? Product. Are you understanding?
Yes.
That's why we have a straight line. This straight line, it means that the reactants are finished. Understand?
Yes.
So you're going to come across this, and people that just they didn't even throw anything. These people, okay, it's fine. You must draw, you must make annotations. I won't tell you that draw, write, what. I usually tell the kids that I teach that you write the things that I say. Well, good, right?
Yes.
Did you understand what this straight line means?
Yes.
You know, someone, if you don't want to write reactants are used up, you know what you can say? No more product are being formed. We're continuing. So now, I'm introducing, it's not really something new. Now we understand this graph, what is happening on this graph.
Yes.
We understand that this straight line, it means products are no longer being formed, right? Okay. Now we want to talk about where is the rate of reaction? Which graph is the rate of reaction the fastest? You come across such questions, right?
Yes.
They draw something like this. Look at it. A, B, C. You see? Change in time, then molecules. You see A, B, C. They ask, which one is the rate of reaction the fastest? Which one is the rate of reaction the fastest? Which one?
C.
C. Incorrect. Incorrect. No, when you say C, you will say B. That's crazy. Okay. Let me teach you, right?
Yes.
You know a bicycle. Bicycle.
Yes.
You know it?
Yes.
My bicycle, make handy, my make handy,
Yes.
you need that, need like a share lily. I shall let it fly. My one, you really should go 6 degrees. Mas one, Kala, Nala, if we basket ring at that, at least 7 1 even 8 1. This rain, if we go 1, 2, 3, if we basket ring at that to one, you know? If I go each rather than I was waiting. So, one basket if I'm going to that rate of reaction, that's how you determine it. When I look back on the question, I'll check it. Let's run up you know what you must think about basket. What's on the question of basket? You think about what? Bicycle, you get the answer. John, you know basket. Don't take a basket, ni bekela. I think ana like a fan. Take a basket, ni bekela. Ni one ni bekela. He got that to my wolf. Matter why? At A, the rate of reaction is the fastest. Why A? Because A has a steeper gradient. Any gradient subla shiganga so steep subla lokushte e. Loku say shite e ngoku. Subla kushijani steeper. English is not our language, right?
Yes.
So we must even tell you these words. So shiganga loku shigange kingo for steep. Loko xiganga se xi tshinela ka ku va straight xi famba na xi lexi hi xi too steep must you see that? So the rate of reaction is more faster where there is a steeper gradient. What is steeper gradient? Cecily, you know, what is this? Steeper gradient. Look, xiganga xi ta enga. What's going on? What will happen? The rate of reaction will be faster. Basket is faster. It has to mango. Are you learning?
Yes.
So it means here, A, the rate of reaction is faster. Why are we saying the rate of reaction at A is faster? It's because it has got a steeper gradient. What the numbers of the man? Wabola shinga to tumingo kulan, kutula la. Imakaku, this one shiganga. She ended that. She clearly moved Maswana. It is not steep, it is less steep. You understand?
Yeah.
So this one is less steep. Said the rate of reaction is fastest here. Why? Steeper gradient. Did you write somewhere?
Yes.
You wrote, ne?
Yes.
Okay, that's lovely. Are you learning?
Yes.
Okay, let's continue. We're good, right? Let's just quickly just talk about factors that affect the rate of reaction. Rates of reaction. We know them very well. I know that you know them. Right? I just want to put some flesh on it. The first factor, okay. Let me list them here. I'll list them here, then I talk about each one by one here, right? We know the first one, surface area. Surface?
Area.
The second one, temperature. Temperature. The third one, concentration. Concentration. The fourth one, catalyst. Catalyst. The fifth one, nature of reactants. I'm not interested in nature of reactants. We'll emphasize those four. Are they four? And many more, right? Let's talk about surface area. Surface area. Ladies and gents, when we talk about surface area, we're talking about the space. Look. Surface area is a what? Space. You see this space here where we are in this mobile class. This space is larger. It is big, right? It means there is a larger surface area. When we talk about surface area, we're talking about what? Space. Surface area is?
Space.
So it means, remember, rate of reaction is concerned with what? With the reaction occurring faster or slow. So, isn't it, you find that you are working in a company, right? You are selling maybe a particular product, right? You are interested in making sure that you get your product that you manufacture fast. You understand? You want to make the product to be produced faster, right? It means you are concerned with the what? The rate of reaction. Rate of reaction is concerned with what? Reaction occurring faster. So there are factors that cause rate of reaction to be faster or to be slow, right? And the first factor is what? Surface area. So what we'll address a rate of reaction being made fast. How does surface area make a reaction to be faster? After explaining everything, I will explain Maxwell-Boltzmann graph, right? You'll understand. There is a linkage between the graph that I drew initially and what I will explain here. You will see. How does the surface area affect the rate of reaction? On the surface area, I said is what? Space. Right?
Yes.
Okay. There is what you were taught called collision theory. There's what you were taught called collision theory. Collision theory just addresses only two things or three things. You know what it says? It says in order for a reaction to occur, molecules need to collide effectively. Do you know that?
Yes.
So, collision theory by itself, there is no question that you are going to come across and it wants you to explain collision theory. You will use collision theory to explain the factors that affect the rate of reaction. Do you know the types of collision? Yeah? Okay, collision theory. Let's just quickly go through it. Collision theory. Listen, you see this collision theory, you won't be asked that explain collision theory. You will use collision theory to explain this, right?
Yes.
So let's just write the points so that when we explain these points, we use them in this. You know, the first point it says that we've got two types of collision. Two types of collision. The first one is effective collision. Effective collision. When we say something is effective, what is happening? When we say something is effective, something that is effective, it means it works, right?
Yes.
Yeah? It produces good results, right? When we say effective from English point of view, we're good. Then we have ineffective collagen. Ineffective collagen, it means it does not produce result, right? It is not good, it is ineffective. It does not work. When you say something is ineffective, it means it does not work. Effective, it works, right? Yes. Guys, so when we talk about, am I fast? No. Okay. When we talk about collagen, it's simple. This is collagen, you see? Collagen, okay. Let's just explain what is an effective collagen. Formation, yeah, the product. Must you say that? Is the effective collagen is a type of collagen which results in the formation of new bonds. Must you say that? Do you see this duster and the calculator? They are colliding, right? This collagen, is it effective or ineffective? Ineffective. It does not produce anything, right? It does not produce anything, right? Because it is ineffective. Let me show you an effective collagen. Do you know juice? Juice. I take juice fusion, right? Juice in cleaning money. Juice. Utayibona juice irioshe ya fusion la kumbe Wild Island la yandeni. Utobosuri juice yonweka isona. Shulaku, what happened there? Effective. Okay, sir.
And also,
okay. You see this thing of effective and ineffective collagen, right? Yes. Collagen theory just talks about that. We have effective and ineffective collagen, right? Yes. The last statement we can say, in order for a reaction to occur, right? Yes. Molecules must collide effectively, right? Yes. Effectively. So it means if the rate of reaction is low, molecules are not colliding effectively. You understand? Yes. If the rate of reaction is low, molecules are not colliding. Oh, that collision is very slow, right? Yes. Because surely each and every reaction, in order for it to occur, molecules must do what? Collide. This is collision, right? Yes. So sometimes molecules, they collide, you find that the collision is occurring slowly. And when the collision is occurring slowly, what will happen? If the collision is occurring slowly, what will happen? It means the rate of reaction will be slow. Rate of reaction is the reaction occurring faster or slow. Guys, do you know corrosion? Do you know corrosion? Corrosion is rusting. You know rusting? It takes time for something to rust. Do you know that? Do you know that there will be a time where this metal is going to rust? Yes. And the rusting is occurring, but you can't see it, right? Yes. Is the rate of reaction fast or slow? Slow. It is slow, right? Yes. Is a molecule colliding fast or slow? Slow. They are colliding fast or slow, right? Yes. We are good about collision theory, right? Yes. So they will not ask you to state this alone. You will use this with the factors. Let me show you how we use that with the factors. We are good, right? Yes. Okay. Collagen theory. So now, let us talk about surface area. How does surface area causes the rate of reaction to be faster, right? Yeah. How does surface area causes? On the surface area, I said is what? Space. Space, right? Yes. Come. Quickly. Come. Come. Let's stand. You see us, right? Yes. Let's say I say we must move each other by fists. Ne? Yes. Since we are very close, will the fists be painful? No. Huh? No. But so close, right? Yes. It means it's a collision effectively where we've got small space. Because this space is small. Can you see? Yes. The space is what? It's small. Isn't it a fist is a collision, right? Yes. I need to collide these two, just like this, right?
Yes.
So it means there's no space for the fist to collide with me, right?
Yeah.
Okay, let's create space. Let's say I say we must mold each other with this. Let's say I say we must mold each other with what? With fists, right?
Yes.
Will we feel a lot more pain?
Yes.
We will feel a lot more pain because now there is what?
Space.
There is a space, right?
Yes.
It means space affect what? Can cause the rate of reaction to be faster or slow. Because look, we have molecules, right?
Yes.
Those molecules, they must collide, right?
Yes.
So when the space is larger, it means we've got molecules are going to collide effectively because there's a larger space, right?
Yes.
So when we talk about surface area, we said surface area. We say an increase in surface area will cause what? There is enough surface area for molecules to collide effectively. And what I love is that this thing they do not change. They will set one of these. It's either temperature, concentration, catalyst. You need to know which one is that. Guys, I've demonstrated to you that in order for effective collision to occur, we need enough space, right?
Yes.
I demonstrated that through what? Through fists, right?
Yes.
When we are closer together, when molecules are closely packed, do they have enough space for them to collide?
No.
They don't have enough space for them to collide, right?
Yes.
What about when the space is larger? They can collide, right?
Yes.
They can collide because the space is what? Is larger. Do you understand how surface area affect?
Yes.
So it means if I have two molecules, right? Or I'm performing experiment, right? I'm performing experiment. Here, there is a what? Here there is a larger surface area. Here there is a smaller surface area. Which one will have the fastest rate of reaction? The one where there is a larger surface area, right?
Yes.
Why? Because there is enough space for molecule to collide effectively. So if the space is small, it means the molecule will collide ineffectively. Are these people learning?
Yes.
Understanding, eh?
Yes.
Okay, you must copy this because I'm about to give you secrets. Secret. This is a secret. Don't tell anyone. I'm serious. Okay. But what I'm demonstrating now is not a secret. It's another demonstration. Do you see this? Do you see this, right?
Yes.
Okay. You see this chalk? It's a piece of chalk, right? You can see this. It's a piece of chalk, right? It's this chalk. Nothing has changed, right? You see, I've put it here. I put it here, right? It has taken this small space. Can you see?
Yes.
It is this chalk, right?
Yes.
Look now. Look what will happen to the chalk. You see the space it has occupied? Let me see. Let me break it. I break that chalk, right? Did it take the same space? Is the space now that it has occupied, is it small or larger now? It's larger. I'm so long to put something to chalk on to Ali. You're going to guide to my map, and just spread. I must want. You know what that means? It means that if we have something which is in granule in Ghana, something which is in granule, so we have a tablet. Tablet, a pills, my own pills, you cannot tablet, must do one. Tablet, subula rigi, a subula pills, Africa University, tablet. Tablet, the subula she should be a sofana rigi, so on. Tablet. Tablet, there are phone. Tablet, subula she should be a Muslim. Setana. If I can have this chalk, which occupy this space, and I take the same chalk, and I grind it, right? When I grind it, you know what I've done? I've increased the surface area. It means the rate of reaction is faster where there is a powder. The rate of reaction is faster where there is a powder. And rate of reaction is slow where there is a tablet, where there is a granule, where there is a solid. You understand?
Yes.
Between a solid and a powder, which one is the rate of reaction faster? Powder. Why? Because when I make something to be powder, did you see what happened?
Yes.
The very same chalk is started to occupy a larger space. It means I've increased the surface area, right?
Yes.
When I increase the surface area, what did I do? It means there is enough space for molecules to collide effectively. Let me just give you, do you know an ice? Yes. You know an ice, right? Inside the fridge, you know the ice is what? Is the molecules in the ice are closely packed. Do you know?
Yes.
Molecules don't manyana. Is there enough space for molecules to collide?
No.
There's no enough space for molecules to collide, ne?
Yes.
Do you understand how does these things of space work? Do you know how surface area affect the rate of reaction?
Yes.
Did you see the demonstration? If they bring something which is solid and something which is powder, the rate of reaction will be faster when there is a powder, right?
Yes.
Because on a powder, the surface area is larger. Are you learning?
Yes.
She's a lesson by this one. Okay. Those secrets are coming, right?
Yes.
You don't share them with anyone. These are factors that affect the rate of reaction, right? For surface area, I will say there is enough space for molecules to collide effectively, right?
Yes.
Look at this point. Look at this point. More effective collision per unit time. Per unit time. It means within a space of time, molecule will collide, and all those collision will be what? Effective. You understand?
Yes.
More effective collision per unit time, right?
Yes.
Then I will say many molecules with EK greater than EA, because I don't have space, you will say many molecules with kinetic energy greater than activation energy. EK is kinetic energy, EA is activation energy. So it means when there is when we have enough space, it means what will happen? There will be many effective collision per unit time. Because there is enough space, it means effective collision will be many. That's what it means, right? Yes. Effective collision will be many. Are you learning?
Yes.
Then we come to this last one. It means we will have many molecules with kinetic energy greater than activation energy. Can I tell you the secret?
Yes.
Here is the secret. What's it? I need that cheat now. Unga the surface area. I put the eye cheating. Now go blow the area you want. What is this and that? For some rabbin, the rabbin is also like that. I'm not under concentration. Now, let him be rabbi change. Needs a temperature, let him be rabbi change. Needs a catalyst, let him be rabbi change. So now the different translator affect the rate of reaction. What's a therapy in me? The tone of that star. What have got I forget what I got. You want to say, let that be running. What compare at the cheat? So, what can factors that affect the rate of reaction? Any other question? Wow, Steve, no, I'm like temperature, one, I'm like concentration. Oh, Queen, many effective collision per unit time. Many molecules with EK greater than EA. We don't know what the marks is shown. I think change the video. All right, Danny. Push up. Mashallah, all right. We look down there, Mashallah. You see what is happening? Come and tell me that in the Ninja. So that the factors that affect the rate of reaction could be about the wine. She went 10. So that is very what's allowing more effective collision per unit time. Masutan? And that's also yellow and so on. It's also not to feel that's so far and so on. That's also. All right, the phone, I did change it. See, you was one who information in my look at the game. Look at the game. So we have the Galileans one, the Gutala, but total. Where I take our full one. So loko va pfumelela va ku swi ta endla ku relaxa u ta kuma ti nga 89 yi le henhla 89 mara a yi teki award wa swi vona u ta kuma ku xikwembu xi ku nyike vuswikoti swo a fanele u ya teka award kulukwana mara hi mhaka vanhu va ku praise u relaxa u nga hayi u ya yi teka so mi dyondzisa vana van'wana va ta va kuma ti nga hi term 1 va ta ku ti nga the highest a ku 95 a rongi 5 maswo se u nga pfumeli na swi ta ku vanhu va ta swi endla mara wo nga pfumeli wena u nga relax you don't relax we want the best out of you the best of the best you hear me short boy okay talk about temperature between ku surface area ya fika njhani swa surface area ya swi kota ku endla ku rate of reaction yi endla njhani yi va fast loko space xi ri so hina hi ta endla yini hi to xi kurisa loko xi kurisa swa the rate of reaction yi ta va njhani fast aswa look don't do this okay temperature do you know temperature bona do you know an ice loko ni ti tekela ice ya mina ma yi vona ni teka ice ni veka kwala ma swi ka hisa la ni veka la ice ani yi ta endla yini ata wa yin'waka hi mhaka ku temperature ya laha ni le ndzeni ka fridge ta hambanini ya laha yi le henhla swi la ku ice leyi yi ta va kha yi gaina temperature so the ice will be gaining temperature is on you know when something you know what will happen must ku mati ma famba ma swi kota ku famba mati mara milenge u kuma ma nga ha ri kona u ma chele ndhawini ma tshemba tshembe ku mati u nga ma chela ndhawini hlamala ayi kwihi mati ma mina look at this we take a pot right we put water inside and then we take that water and we put on the Bunsen burner or fire right you see what temperature will do temperature will cause molecule to gain kinetic. You know kinetic energy is which kind of energy? Energy of movement. You'll see water starting to even sing. It's water, ne? Ukuma mad and my melon. Ukuma eta mad masula kuchini. Awenda michu because of temperature. Temperature is dangerous. After masula masula kwenda kule. You just increase temperature, so man. Kinetic energy is the energy of movement. When you increase temperature, you will see even water starting to do what? Starting to move. It means water have gained what? Kinetic energy. Kinetic energy is the energy of movement, right? Yes. Water will start to move because you increase the what? Temperature. You come back after an hour, you find that there is no single drop of water. Do you know it's possible? Yes. Water can evaporate and it moves. All of it. Are you learning? Yes. So it means how does temperature affect the rate of reaction? So increase in temperature. Temperature will do what? Will cause the molecules. You saw the molecules to gain in. To gain kinetic energy. To gain kinetic energy. So they gain kinetic energy, then they collide effectively and collide effectively. Will gain kinetic energy and do what? And collide effectively. It means when you increase temperature, molecules will do what? Will gain kinetic energy. They will start to do like this. Kinetic energy is the energy of movement. Yes. Now, when you come move, it's energy now. It's kinetic energy. How good? Yes. When you increase the temperature, the molecules still gain kinetic energy. This will not move. If you come move. Tell them, the banana. And it's certain energy of banana. Look, there are energy, kinetic energy of farmer. Get that banana. What's one? When you increase temperature, you're causing the molecules to gain what? Kinetic energy. And when they gain kinetic energy, they will do what? Collide effectively. Look, say the molecules still now high kinetic energy. Put that in. When the collision total no time, so many effective collision in no time. Many molecules with kinetic energy greater than integration energy. That's what I'm saying. John, it's funny, What you try to say this morning? Can I continue?
Yes.
Let me talk about concentration. Because my wish is if you can go and then you can see Mr. N. Okay. Concentration is on. Kuraba whiteboard mother and what on in the transition. Concentration is on. After concentration to like. My dear Jews on. Jews. I know you never one. Jews. My one. My what? Why the island? This is how you make it, Sunny. Nama, that's on. Loco. Before you mix the juice, we say it is concentrated. It is concentrated because it is dark and it has got many molecules. You understand? Let me just give you an example. These are molecules of juice, right? These are molecules of juice. Look at these molecules of juice. Can you see? Do you see this? Between this one and this one, which one is concentrated? It is concentrated because it has got many molecules. You understand? Yes. So this one is concentrated. Ani collagen. Bona. Also an collagen amon between here and when I come and stand here, which side is concentrated? How many molecules are? Think I hope. When the concentration is high, I increase the rate of reaction. And increase the molecules the collagen. Can you see?
Yes.
Do you see that?
Yes.
When we increase the number of molecules, it means we have increased the what? The collagen, the chances for collagen to occur. Are you learning?
Yes.
It means that you get a lot of molecules, you get a lot of the process, you tell them, so what do banana even rate of reaction in the fast? Maralogo, Joba the rate on or don't you tell me that few, right?
Yes.
When I'm 2 1 2 banana, to that banana. 2 1 to that banana, 2 banana, rate of reaction is low. There's ineffective collagen. Can you see?
Yes.
Because the concentration is low. Well, decreases the chance for collagen. But here, oh, how about the banana? I need the men. Hello, I mean that picangi moon. You couldn't walk on us and take a moon. They know that would see it, but they don't hope. Because there are many molecules. It means concentration will cause the rate of reaction to what? To be faster.
Yes.
Concentration. So it means concentration is on. It means increase in concentration. Many molecules with kinetic energy to collide effectively. It means when we increase concentration, it means we have increased the what? The molecules, right? Yeah. And those molecules that we have increased, they have got what? Kinetic energy to collide effectively. When the molecules are few, it means I've decreased the molecules. Do you understand how it affects the rate of reaction?
Yes.
Then the point that will come here, more effective collagen per unit time. The last one, many molecules with kinetic energy greater than activation energy. Alright, Ali?
Yes.
Yeah, the blood like catalyst again. Alright. And concentration long get the molecules. Look, you get the increase the chance to get by as one. I thought that was so get by. Okay, one. And now, blood like the factors that affect the rate of reaction is on. I really catalyst here, are you? Catalyst. Catalyst, all right, man?
Yes.
What a catalyst, you know what's a catalyst? It's a substance that speeds up the chemical reaction without being consumed, right?
Yes.
According to exam guideline, how do they define it? Listen, the definition for catalyst, it is examinable. You need to know it. Can you give it to me? Substance without undergoing any permanent change. A substance that is doing what? A substance that speeds up chemical reaction without undergoing a permanent change. You need to go and study it. Masutan catalyst. Okay. Koga ku anlaboni amhlisa susarongo mara athetha mandoza susungata. Wow, I wonder what to do. I want to know it. I'm not like a Thailand. Catalyst. We're fine, right?
Yeah.
How does the catalyst causes a rate of reaction to be fast, honey? A catalyst, it is a bit complicated. Okay? Let me just draw this. Is this one endothermic or exothermic? It is endothermic because energy is gained in the system, right? How do we see? This line represents reactant, right? This line represents product. So it means we started with a small amount of energy and we end up with a high amount of energy. It means we gained energy, is it?
Yes.
Does it make sense?
Yes.
So this one is endothermic, right? Because we started with a small amount of energy and we end with a high amount of energy. You understand?
Yes.
So what does a catalyst do? A catalyst, let's say we have a reactant, A plus B, né? You add the what? A catalyst, right? Okay, let me just give you an example. I add A plus B, né? And a plus what? Plus a catalyst. Which symbol can I use for catalyst? Let me add cat. Let me write cat so that I don't confuse you. You know what will be produced? C plus D plus cat. Cat will never be lit up. It's not part of a reaction. It's just there to speed up a chemical reaction. You understand? It will never be eaten. You see, A and B were eaten to produce C and D, right? But a catalyst will do what? Will never be eaten by a reaction. You understand? It will remain like that because it's a substance that speeds up chemical reaction without undergoing any permanent. It's like at home when they are cooking. What do you call that? Bush? Yeah. When they are cooking bush at home, right? Yeah. Because those leaves, they are harder, they are not soft, right? They need to be cooked for a long time. So when you put cooking soda there, you know what will happen? The cooking soda will cause that process to be more faster, right? Also that thing of cooking soda, when you eat it and it causes the rate of reaction to be faster in your stomach, is the example of a catalyst. It causes chemical reaction to be faster. You understand? But it does not consume, it does not get consumed by the reaction. You understand? So how does a catalyst causes a rate of reaction to be faster? Ne? We know this thing. Here is called the activated complex. Complex, ne? Then this is reactants, right? Reactants, this is product, right? Then this is activation energy. I call it EA. Activation energy. Is there someone who have a car here? Not a car which you were given, the one you bought by yourself. Do we have? No one, eh? You know why? You know why you don't have cars? No. It's because it's expensive, right? Even your lunch, the money which you are given to buy lunch cannot be enough for you to buy a car, right? Yeah. Let's check, I do this. I make a car to be 50 rand. Car. Imagine a car is 50 rand, right? Will we have people who do not have cars here? No. People will go and buy cars because they're cheap. The last thing is on that. Because we decrease the price, right? Yes. We decrease the price of what? Of cars. You understand? Yes. What did we do? We decreased the price of cars, right? Yes. So since we have decreased the price of cars, everyone was going to go and buy it. Let me talk about activation energy. It's the same thing. Ne? Activation energy is the what? Do you know the definition of activation energy? You need to know it, the minimum amount of energy needed for a reaction to start. In other words, activation energy, a reaction will never start without getting the activation energy. It's the energy that does what? That activates. So in order for a reaction to start, it must be activated. In order for a reaction to start, it must be activated. So the reaction will never start until it is activated. You understand? Yes. So activation energy is the minimum amount of energy needed for a reaction to start, right? Yes. So here are numbers: 20, 30, 40, 50, 60, 70, right? In order to reach this activation energy, what do you need? You need to gain energy in your system. That's then the reaction is going to start, right? So it means it will be, let's say you need 50 joules. You need 50 joules for a reaction to start. Before you get 50 joules, the reaction is not going to start, right? You need the 50,000 to buy a car. Before you get 50,000, you won't buy a car, right? Yes. You know what catalysts do? Huh? Catalysts start. They need 50 joules. No, man. That is too much. Catalyst will come and decrease this. You see this 50? Catalyst will make it 10 joules. So if it is 10 joules that is needed for a reaction to start, it means it will be easy for a reaction to start, right? Because we no longer need 50. Catalysts have made sure that the activation energy is what? Is 10. Then it will be easy to start that reaction, because to gather 10 joules, it is more easier than to gather 50 joules, right? Then the reaction will start. So this is what catalyst. Sometimes question will come and say, show us the effect of a catalyst. Here's the effect of a catalyst. You draw a dotted line. That dotted line, you come up with this peak in Tabale, and you will say figure. Look, Tabale say you will figure. It is easy for reaction because we have decreased the amount of energy that was needed for a reaction to start. This amount. Then it will be easy for a reaction to start. You understand? Yes. What does the catalyst do? It reduces the activation energy. Catalyst reduces the activation. Yes. So in order for a reaction to be activated, it will need what? A small amount of energy. Are you understanding? Yes. So did you see? A question will come and say, show us the effect of a what? Of a catalyst. A question is going to come and say, show us the effect of a catalyst. You know what you do? You draw a dotted line. Dotted line. Dotted line if I dotted line if I ishi shofana shesh koba ku drawing yakona senjani you ngitwi activation energy masibona. So that's how a catalyst increases the rate of reaction, right? So let me just do it in writing. It means catalyst will do what? Catalyst will reduce. It will reduce the activation energy. Catalyst will reduce the activation energy, right? So like when the activation energy is reduced, there will be what? Many effective collision per unit time. Many molecules will have kinetic energy greater than activation energy. And I told you, we always write them. Yes. We are good? Yes. Okay. As I'm saying that, sometimes the problem is that when you are given a question, kids, they fail to decode which factor are they talking about in a particular scenario, right?
Yes.
Okay, let me show you this. Let's say we have the experiments. Experiments. Right? Experiment. Okay, experiment 1. Experiment 2. Experiment 3. Okay. Okay. Then we have temperature. 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 Then we have concentration. Concentration. Go on. I'm on funny thinking. Temperature 20, 25, concentration 0.3, 0.3, 25, 25, 0.3. Is that on it? All right. Okay. Tell me, between experiment 1 and 2, so this is the problem. When they say between experiment 1 and 2, people will look at everything. When they say between experiment 1 and 2, what do? You leave this one. This one is not there, right? Yeah. You look at these two. Do you understand, Sako? You look at these two. When they say between experiment 1 and 2, between experiment 1 and 3, it means when they say 1 and 3, you erase this one, right? Yes. Okay, let me ask you a question. Between experiment 1 and 2, which one have got the fastest rate of reaction? 2. Yes. Why do you say 2? First, because there's high temperature, right? It does not end there when you give the answer. What must you say? It has got high temperature. Right, the thing I was teaching you. Experiment 2 have got the fastest rate of reaction. The first thing, why? Because it have got high temperature, so on. An increase in temperature, it means it have got many molecules with kinetic energy to collide effectively. More effective collision per unit time. Many molecules with kinetic energy greater than activation energy. And it comes with 3 marks. So that's how you get to answer this thing. But, oh, this one has got the fastest rate of reaction. You give the 3 points that I showed you, right? Yes. Okay, let me not record this because it's all. Now I want us to explain the Maxwell-Boltzmann graph. I want to explain the Maxwell-Boltzmann graph because we were just talking about the factors that affect the rate of reaction, right? Yes. So it's very important because that is related with Maxwell-Boltzmann graph, because there is a Maxwell-Boltzmann graph for concentration, for temperature, for what, but it's the same graph. It's just one and the same thing, right? Yes. So here we have got molecules, right? Yes. Then here we have got what? Okay. Eh? Surely you've seen a graph, something that looks like this, right? Yes. Then we have another line here. You see, this line is called activation energy. It does not look nice. Let me just draw a nice graph. It's very important to draw nice things, right? Yeah. Yeah, this one is better. Then we've got EA. You see this EA, it represents activation energy. Then they usually make this area to be darker, but it doesn't have to be darker. It is darker just for the sake of explanation. But what is important is just that you need to see this one, this way, and you need to see this one. Surely you have seen this graph. It's called Maxwell-Boltzmann graph, right? Okay. We've got curve A and curve B, right? They say between curve A and curve B, which one, these are molecules, right? Between A and B, which one was is showing a recording at a high temperature? Huh?
B.
Why? Why are you saying B? Can I say those who are saying B? Those who are saying A? Those who are saying A? Those who are saying nothing? You are still saying nothing. Where are you from? Where are you from, my baby? Huh? She's from Goat. What's that? She's from Butaibu.
Yes.
Oh, you're from Butaibu. What's in Butaibu? No, it's. Oh, she's in her own school. She was supposed to be in my school, this one. Because she's from Butaibu, right? Yeah, what's the word okay. I'm kidding. Okay, let me explain what's it. Right? You are right. B is the one which was is showing a recording of high temperature, but since you can't explain that, let me explain what is happening. You see A, you see B. A have got many molecules. It is true. A have got what? Then here we have activation energy. Can you see this activation energy? The problem is that from this line, this side, the molecules that are this side, you see, they haven't passed the activation energy. It means EK is less than EA. These molecules, their kinetic energy is less than activation energy. And when kinetic energy is less than activation energy, it means there won't be any effective collision. You understand?
Yes.
These molecules, yes, A have got many molecules than B. Can you see?
Yes.
The problem, these molecules, they are just useless molecules. They are what?
Useless.
They are useless because they don't have kinetic energy and they have not passed what? Activation energy. You understand?
Yes.
So, yes, A have got many molecules, but these molecules, they are what? They are useless molecules. Please, don't use this language. I'm just saying useless so that you grab it. Ne?
Yes.
We don't want you to go and write home useless molecules. That mistake will move you when you write useless molecules like that. Oh, but what I'm bringing home is that these molecules, they have what? Less kinetic energy. The kinetic energy is less than activation energy, meaning that these molecules, although they are many, they cannot collide effectively. You see?
Yes.
That's why for Maxwell-Boltzmann, when we look at the graph and make judgment, we don't look at this. We look this side. Can you see this side?
Yes.
The molecules that are here, they have passed what? Activation energy. It means this one, they've got kinetic energy which is greater than activation energy. So these ones, the activation energy is not yet reached. You understand? Molecules here have got kinetic energy less than activation energy, meaning that they won't collide effectively. So when we look at this, we look this side, right? Let us look at B. Look at B. You see B. You see B, right? Yes, B. You see B, no? So it means B, when we check, B has got, you can see B is above what? It's above A. Can you see? There are numbers here, guys. 2, 3, 4, 5, 6. There are numbers, right? So it means this one, which is B, it records a high number than what? Than A. Can you see?
Yes.
So what does it mean? It means B have got many molecules with kinetic energy greater than activation energy. And remember, if the molecules have got high kinetic energy and which is greater than activation energy, it means they will do what? They will collide effectively, right?
Yes.
So since this one are many, it means the rate, the one which can represent where the rate of reaction is fast is B. Why? Because B have got what? Many molecules with kinetic energy greater than activation energy when we compare it with A. You understand? Sorry.
Yes.
Although A have got many molecules, but the problem, there are many these molecules, but problem about these molecules, they are not useful. They do not have what? Kinetic energy. You understand?
Yes.
So which curve was obtained at high temperature? Curve B. Why high temperature? Because at high temperature we've got many molecules with kinetic energy greater than activation energy. You understand?
Yes.
Which one was achieved at high concentration? B still. You understand?
Yes.
High concentration, it means there are many molecules with what? Activation, with kinetic energy. You understand? Which one, there was an addition of a catalyst, the same thing. You understand what I'm showing you here?
Yes.
So for Maxwell-Boltzmann, we come and look this side. You can see that B is high, and the molecules that are here, that what? They have got kinetic energy greater than activation energy. So that's how we explain Maxwell-Boltzmann graph. Is it difficult to understand?
No.
You understand?
Yes.
Okay. I'm happy now. It means we can go to rates of reaction. Very correct. What she's saying. No. It's very 100. Listen. She said, I said equilibrium, right? She said it's a chemical reaction where the reverse reaction is equal to the forward reaction. It's incorrect because you left the correct words, right?
Yes.
It's a chemical reaction where the rate of the forward reaction is equal to the rate of the reaction. Now, Bawan, look, Wabla, share so mean, I don't know. The rate of the forward reaction is equal to the reverse reaction. If I put the rate, the rate of the forward, because the common mistake that we make, we say it's a reaction where the reverse reaction equals to the forward reaction, and we need to say the rate of the forward reaction is equal to the rate of the reverse reaction. We're good, right?
Yes.
Are we fine?
Yes.
Okay, let us do whatever we're doing and we finish. We're good, right? Okay, I want to demonstrate something to you. Now, I'm going to draw a graph for the equilibrium for you, right? Okay. Let's say we have this. Just a simple graph, right?
Yes.
Equilibrium. When we talk about what? These things of equilibrium. When we talk about these things of equilibrium, I